All right, continuing on with, I guess, part two. We're now on question 30. So sand is pouring out of a container, and the remaining amount of sand is modeled by that equation where t is in hours. At what rate is the amount of sand changing at 4 hours and 30 minutes? So the first thing to realize is that 4 hours and 30 minutes is another way of saying t equals 4.5. And we want to know how the rate in meters cubed per hour is changing. And in other words, think about this. If we have a function that currently takes in hours, we want to know, and it gives us meters, and we want to derive and get meters per hour, then what we're really doing is we're asking you to find s prime of 4.5. Because if s's units are meters and our independent variables units are hours, then deriving gets us meters per hour as a unit. So all we have to do is derive this, and we get negative 2t. And so if we plug in 4.5, we're going to get negative 9, and let's see here, meters cubed per hour. And now we want to find where a graph is concave down and increasing. So first let's take care of the increasing part, because that means we're going to need to know g prime, which is negative 6x squared plus 24x. And let's factor that out. We can take out a negative 6x, and we'll be left with x minus 4. So g prime, its important values are at 0 and at 4. And if we make a quick sign chart of g prime, since it is a negative quadratic, we know a negative quadratic is going to look like this. All right, in other words, a negative quadratic will be above, between 0 and 4, but will be below, to the left of 0 and to the right of 4. Or you can, again, always plug in those test values. Try plugging in negative 1, try plugging in 1, try plugging in 5 or 10 or whatever you want, and you'll see that these signs come out as well. Now we're going to investigate where g is concave down, and that means we want to know essentially g double prime. And g double prime, let's go back to the unfactored polynomial, would be negative 12x plus 24. And one thing we could do is we could put both of our sign charts in the same, on the same side. So sometimes we do like numerator and denominator. And since we just have g prime, which is one polynomial, and g double prime, which is one polynomial, we could put them over each other, maybe to investigate where it's concave down and increasing. So g double prime, if you kind of factor this or look at it, you'll notice that it's 0 at 2. And to the left of 2, if you plug in something like 0, if we plug 0 into this, we'll get a positive for g double prime. And afterwards, we'll get a negative if we plug in something like 3, 4, 5, or 6, or 7, or so on and so forth. So again, the question was, where's g concave down and increasing? And so that means, where is it increasing? Here. Where is it concave down? Here. So where is that overlap? Well, between 2 and 4. That's where our graph is concave down and decreasing, because that's where these two overlap. All right, up next, we have a particle question, and we want the time where the velocity is 0, and we were given its position function. So if we want to know where the velocity is 0, we just need to derive position. So we need s prime of t, which is going to be a product rule. So I'm going to keep, what am I going to do? I'm going to think of my first function as 15e to the negative t. Hello. And so I'm going to keep that whole first function, and I'm going to derive cosine, which is negative sine. Then the product rule adds, and now I'm going to derive the first function, which will be negative 15. In other words, a negative is going to drop out from the chain rule. And then just times cosine of t. All right, now let's see here. We can kind of deal with this here and just make that read as minus 15e to the negative t cosine t. And so it looks like what both of these have in common is a negative 15e to the negative t. So let's factor that out. And we're left with sine t minus cosine t. Now we want to know where the velocity is 0. Now this is the velocity function, so we want to know where this is 0. And just remember, exponentials, if they don't have anything added or subtracted to them, then this does have something multiplied to it, but there is nothing adding or subtracting, so this is never 0. An exponential always has that asymptote at 0 unless it has something added or subtracted to it, not multiplied to it. So that means we're looking for where this is 0. And if you set this equal to 0, the other way of saying that is where is sine of t equal to cosine of t? And this is now a unit circle question. Where are sine and cosine the same values? And there's two places, right here and right here. So t could be pi over 4, because that's where both sine and cosine are root 2 over 2, so that's where they're equal, or at 5 pi over 4, right here in quadrant 3, because that's where they're both negative root 2 over 2. Now, this does also repeat for every 2 pi n, but we'll probably give you a boundary for, we won't accept all these, maybe just 1 or 2, or, remember, it could also be, if you add 2 pi to this would be 9 pi over 4 once you go to pi over 4 and take another loop, or you could have 13 pi over 4 if you add 2 pi to that, or, it just goes on forever and ever and ever. But those are the first two on the unit circle within 0 and 2 pi solutions for where s prime of t equals 0. So it does end up being a unit circle question and a product rule as well. On to 33. We want to use linear approximation using the line tangent to f at pi. So in other words, we're trying to estimate 3 by using pi, and that might feel weird until you look at what our function is. The reason we're using pi to approximate 3 is because pi actually works really nicely with trig functions. So let's find the y value. Let's find f of pi. So we have an x, that's pi. We need the y. So that would be 4 sine of pi minus 7. Now sine, the y value at pi is 0. So our value is negative 7. So now we have our y value. And now we need our slope value. So let's find f prime of x. F prime, if we derive sine, we get cosine. So f prime is 4 cosine of x, and the negative 7 derives to 0. And so now we need the derivative at pi. So 4 times cosine of pi is really 4 times negative 1. So our derivative, our slope, is negative 4. So now we have an approximation line. It's y minus negative 7, so in other words plus, equals the slope value at pi times x minus pi. All right, and the approximate value here would then be, let's see here, y equals, I'm going to move that 7 over, but 3 minus, I guess 3.1459, maybe that's enough, minus 7. And, I guess I'll just leave it like this. At some point, you'd be able to see through the multiple choice answers what the correct answer would be. But this would turn into some kind of positive value because we have a double negative going on, plus 7. But I'll stop here, and that is, I guess I shouldn't say equals. That's one important thing to remember, because since you're approximating, we'll say y is approximately. But that won't really be a concern since yours is multiple choice. All right, up next on 34. We're supposed to investigate what type of discontinuity is present in this wacky looking function. And the best way to understand what type of discontinuity you have is to investigate left and right hand limits. Because if left and right hand limits agree, then you probably have a removable discontinuity. If left and right hand limits don't agree but you can find their values, then you'd have a jump discontinuity. Or if your left hand limit is increasing forever and your right hand limit is decreasing forever, or maybe they're both on the same side, then you have an infinite discontinuity. So again, the way to identify what type of discontinuity you have is to investigate the left and right hand limits. One thing that's going to make that easier for us is to factor that numerator. Now, because absolute value is involved, once we factor this, let me show you what we get. We get x minus 1, x minus 3 over 5 times absolute value of x minus 1. It can be tempting to want to cancel that x minus 1 out, but since one of them isn't absolute valued, we don't really want to do that. Otherwise, we might miss a few important steps here. So only cancel them out when they exactly match. So we have parentheses here, we have absolute values here. Absolute values are definitely special, so we don't want to mess with them. So let's investigate the left-hand limit by plugging in something like 0.999. If I plug in 0.999, then this is going to be negative 0.001. Now, we always want to actually use the exact decimal value for the one that we're supposed to be approaching. So in other words, since I'm supposed to be approaching 1, I'm going to actually calculate what that is. But when we're looking at another value that's like not near the limit we're just going to actually pretend we just plugged in 1. So we would get essentially -2 here. So the limit is approximately this, over 5 times the absolute value of -0.001. Now from here you can see that these two are going to be the same value, but this is going to be absolute value and become a positive. So look at this. In the numerator we have 2 negatives, which is going to become a positive, and the denominator, our absolute value, turns this into a positive, and so we end up with, since these two are going to now cancel out because they're the same value, we're going to end up with essentially 2 over 5. And, again, try that out, and you'll see that that's pretty much what you get. And now let's investigate the right-hand limit with 1.001. If I do that, again, for this first term, that's going to be 0.001, and that's going to be effectively 1, so we're going to have -2 again. We still have the 5 from before, and now we have the absolute value of 0.001. So this time, this is already positive, so the absolute value doesn't matter anymore, and this is already positive, so those two are going to cancel, and I get -2/5. Now, in other words, here's what this means. We are definitely approaching a definite value. We can see these two cancel out. There's no asymptote behavior here, so to speak. We're just approaching 2/5. The closer you get, you're going to see these negatives, or this negative gets taken care of the absolute value. These double negatives always turn into a positive. You always end up dividing those two equivalent terms, and you get positive 2/5. Here, the further you go, the more zeros you add. You're going to have this be positive, this absolute value is to be positive. They cancel out perfectly, and you end up with -2/5. So the idea here is we have a finite limit from the left, a finite limit from the right, but they don't agree. So this is one of those cases where we have some kind of, who knows what it looks like around it, but some kind of jump discontinuity, because the side limits don't agree, but they can be calculated. All right, now just to say what would an infinite discontinuity look like, remember infinite discontinuities are when your denominator is essentially approaching 0, so you have some finite number over 0. Remember, if you're dividing anything by essentially 0, you're getting very large numbers. But that wasn't the case. We had equivalent values factoring out and some constants left over, so those are going to be finite. And maybe we'll do one more. This next one, 35, is another one of our disguised derivative questions, because when it says find that specific limit, that's the alternative definition of derivative at x equals 3. That's what that's saying. So really what this means is we need to find h prime of 3. So we're not actually going to use that whole limit term. We're going to derive h prime, because we know how to, which is going to be 2 times, watch out for the chain rule, a 3 is going to pop out, and ln is 1 over the original contents. Now sometimes, again, I've started saying this recently, you can also think of ln of anything as the derivative of that thing divided by the original thing. And you could see that this could eventually be written as 2 times 3 over 3x. And here's something else that happens that's kind of special. Our 3's are going to cancel anyways. So h prime is just 2 over x. And now that I know what h prime is, in other words, I've used the definition of derivative to derive this thing, now I'm going to find that derivative at 3. And so the derivative at 3 is just 2/3. And so